Hi everyone. So this is lesson 6. This is the first. This is the last lesson of the first section on thermodynamics. Lessons 1 through 6 will be on the test April 27th. All right. So there's some information up there on Zoom, SI, and tutoring. This will be posted on April 17th. The office hours the Zoom that day will be used for office hours. Then Sapling is due for homework number 3. April 20th through 24th, we're going to move on to kinetics. That's the next section. That won't be on test number 1. It'll be on test number 2. Zoom next week will be used on 420 for office hours, 422 for quiz 1. I'll talk about that in a second. And then 424 for a actual review. Homework for number 4 is through Blackboard. 5 and 6, this lesson will be through Sapling. All right, so let's talk about that quiz. So the quiz will be April 22nd. That's a Wednesday. It will be through Blackboard between 2:40 and 4 p.m. So you have to sign on and do it during that time. If you show up at 3:55, that means you get 5 minutes. So make sure you get there early. There will be 2 problems. One will be an internal energy calculation. The other will be specific heat capacity calculation. The process will be similar as you did for lesson 4, question 3. You have to do it on Blackboard, upload it onto there. So you can do it on a blank sheet of paper, write out the problem. You don't have to have the problem, just how you solve it. Do a separate sheet per problem, name at the top, make sure you write legibly. I will deduct points. Circle the answer, scan or take a picture, and then upload that picture or PDF by 4 p.m. to Blackboard. So you have 2 problems, they do it separately. The questions themselves should take only 15 minutes. You have the rest of the time to actually upload it, okay? So get there at 2:40, get it done, upload it. All right, I will have Zoom that day on April 20th, but it'll only cover lessons 4 through 6, right? Those problems are on 1 through 3, so I'm not going to help you and tell you how to do it while you're taking that quiz. Okay, so you can take the quiz, and then if you have questions, go to the Zoom. Okay, so we have a little bit of a review here. This is of last lesson, which is on entropy. Entropy, remember, is disorder. And so if we are talking about disorder, S, right, and a lot of times we're talking about delta S, the change in disorder for a reaction. So let's look at number 1, condensation of steam to a liquid. If I want to know the delta S for this, what I need to do is I need to actually start off with a reaction. So I'm going from steam. Steam is a word for H2O gas. So we're going from H2O gas to H2O liquid. Which one will have higher disorder? This will have high S. This will have low S. So I'm going from high to low. So that means my delta S will be negative, right? Or less than 0. If you're confused by that, I think we go through this exact example last one. Okay, number 2, we're going from 2NO2 2NO2 gas to N2O4 gas. There was a special case whenever we are dealing with gases. When we're dealing with gases, what we do is, notice we're going from gas to gas, so we can't say that. What we do is we look at the number of moles of gas. This has 2 moles gas. This over here only has 1 mole gas. So I'm going from 2 moles of gas floating around to only 1 mole, right? So this has a high S. This will have a lower S. So again, delta S will be negative or less than 0. Okay, C, we're going from H plus and OH minus to H2O. These are aqueous. Remember what aqueous means? Aqueous means that something dissolved in water. So we're going from aqueous to liquid. So this has more disorder. We have a mixture of things. Here all we have is water, right? So this will be high S. This will be low S. And so again, delta S will be less than 0 or negative. All right, let's do D real quick. In D, 4. In 4, we have a chunk of iron originally at room temperature at 25 degrees C, and we're going to 100 degrees. 200 degrees. Doesn't matter. But what we said was with temperature, if I increase temperature, what I'm going to do is I'm going to go low S to high S. What that means is that the iron in there, it's still a solid, but now it's vibrating a little bit more, right? Those molecules are vibrating a little bit. They have a little more disorder. So in this case, my delta S would be high minus low. That's going to give me a positive or greater than 0 delta S. All right, so that is a little bit of review of entropy. If you're having questions with that, go back to lesson 5. All right, but now let's go ahead and let's move on to lesson number 6, which is on free energy. This will be a little bit of a long one, but it's an important one, and it kind of wraps up everything we've been going through. Okay, so let's remember, we talked about delta U, Q, and W. Then we talked about delta H, enthalpy, and then delta S. Yeah. And last time we also talked about something called spontaneity, right? A spontaneous process is a process that occurs naturally under a certain set of conditions. Okay? It depends on the conditions. The reverse of a spontaneous reaction will be non-spontaneous, and spontaneous does not mean fast. So here we have some notes, right? If I have water and it's in ice form, and I wanted to go to liquid, this would be just water. At negative 50 degrees, ice isn't going to melt. So this would be non-spontaneous. Okay? Non-spontaneous at negative 50 degrees. But this is going to happen at room temperature, so it's spontaneous at room temperature. Right? Here, water freezing is spontaneous at negative 50 degrees C. It will occur. But it's non-spontaneous. It won't occur at room temperature. And we said this came from the second law of thermodynamics, which says that delta S of the universe equals delta S of the system plus delta S of the surroundings. Notice this surroundings. How do I increase the entropy of the surroundings? One way is to actually put energy out into the system to heat up the surroundings. Okay? And so we can change this, and I'm not going to go through the steps, but from this, we can get this reaction. Delta G, or this equation, delta G equals delta H minus T delta S, where G is a term called Gibbs free energy, or a lot of times we just call it free energy. And it's the maximum amount of work that can be performed by a system at a given temperature and pressure. Now, that doesn't quite make any sense, right? Well, it's just, hey, if I had some system and I converted all of that energy into work, how much could I get out of it? But this equation right here is very useful, because what it says is that the change in Gibbs free energy for any system is equal to the change in enthalpy minus T times the change in entropy. And this is very important because delta G is an indicator of spontaneity. If a reaction has a delta G less than 0, so it's negative delta G, that means it's going to be spontaneous. If delta G is greater than 0, that means that it's non-spontaneous. And if delta G equals exactly 0, that means it's a reversible, right? It's going to go both ways. And that means it's at equilibrium. Okay? And that means that the arrow goes both ways. We're going to use delta G a lot in order to tell if something's spontaneous or not. Okay? One tip, right? Notice how delta G tells me about spontaneity. Delta S is entropy. Delta S is not spontaneity, right? So don't confuse those two. Now we can look at this under standard conditions. That means it's at 298 K and 1 atmosphere. And when we talk about that, we add in these little knots here that just show that it is under standard conditions. Okay. All right. So let's move on and let's use this. All right. So delta G equals delta H minus T delta S. So let's say we have some reaction and we're given a delta H and a delta S, and we want to know if it's spontaneous. Well, what we have to do is we need to calculate delta G. So let's look at this reaction under two temperatures. The first will be at 2 Kelvin. At 2 Kelvin, right? So all we're going to do is we're going to plug these into that. So I have delta G equals delta H. I'm told that it's negative 55 kilojoules. And then minus my temperature here. My temperature has to be in Kelvin. It has to be in Kelvin because notice the units for delta S are in joules per Kelvin. So it has to be in Kelvin in order to balance out. All right, and then times negative 200 joules per K. Okay. All right, so when I do this, I get negative 55 kilojoules. And then minus times minus, this is going to give me positive 400. Notice the K will cancel out, and I'll get joules. So when I look at this, I may want to just add these up. But notice the units are different. You know, that old saying, you can't compare apples and oranges, right? I can't add kilojoules and joules. So I need to convert these so that they're the same units, right? So 400 joules, for every 1,000 joules, we get 1 kilojoule. So that's going to be 0.4 kilojoules. Sorry, that's not the final answer. That's just what I'm going to use here. Okay, so I get negative 55 kilojoules plus 0.4 kilojoules. So I do this work, and this ends up giving me negative 54.6 kilojoules. Notice that's different than if I added up just negative 55 and 400, right? I get a totally different answer. So make sure you convert. All right, so negative means that this will be a spontaneous reaction. Whatever this reaction is, it will occur at 2 Kelvin. Okay? All right, so at 2 Kelvin, we said that delta G equals negative 54.6 kilojoules, and it is non-spontaneous. Or sorry, it is spontaneous. That means it's going to occur. Okay, let's move on and let's do part B. In part B, we're now at 325 Kelvin. At 325, I do my work. My delta H remains the same. And then I minus 325 Kelvin. And I'm actually going to do something. I'm going to take my delta S and I'm going to convert it before I use it from joules to kilojoules. So I can just say this by 1,000 joules is 1 kilojoule. And that's going to get me negative 0.2 kilojoules per Kelvin. I can either do it this way or the way I did it last time, which was do that calculation and then do the conversion. Okay, so this number I'm going to put in right here. I showed you how to do that, so let's go ahead. This becomes delta G equals negative 55 kilojoules minus, right, this will become plus because it's that. It's going to get me 65 kilojoules, because notice I already did that conversion, and now this is positive 10 kilojoules. All right, so my delta G is positive. So what does that mean? That means that this is a non-spontaneous reaction. It's not going to occur at 325 Kelvin, but it will occur at 2 Kelvin. All right, let's look at this one more time, and then we'll explain what this means. Okay, so here's the calculation for 2 Kelvin. And I plugged in my delta H. I used my data for delta S. I made sure to convert from joules to kilojoules, right? You're going to have to do that a lot of times, so make sure you're getting used to that. And I got a negative value. I did the same thing at 325, and I got a positive value. Okay, so sometimes I can do the same reaction, but at one temperature it's going to occur, be spontaneous, at the other it won't. That's the same thing with this water here freezing, right? That's going to occur at one temperature, but it's not at another. Okay, so spontaneity depends on temperature and the signs of delta H and delta S. So we're going to look at this, and we're going to see, hey, when is it that that things are spontaneous and when is it not? And in order to do this, we're going to look, and we're just going to say, we're going to look at this delta H term and then this minus T delta S term. Okay? And whether delta G is positive or negative is going to depend on how big those two terms are. All right, so let's say, so I kind of reversed it just to say, so let's say delta H is positive. That means this first term is also going to be positive. Okay? And let's say delta S is negative. Well, that means that negative T delta S is going to be positive. So then, sorry, let me just add a plus sign. If I have a positive plus a positive, that's going to get me a delta G that's positive. So if I ever have a reaction that has a positive delta H, right, that means it's endothermic. It's taking in heat. And it has a negative delta S, that means it decreases disorder. It will always be non-spontaneous, right? This will never be a reaction that will just occur. I have to do something to make it occur. All right, let's say we have a different type of reaction. Let's say we have a reaction that is negative delta H. That means it's exothermic, but it has a positive delta S. Okay? Well, my delta H will be negative, and my delta S, that being positive, means that this negative T delta S term is going to be negative. So if I take a negative plus a negative, that's going to get me something that's always negative. It's spontaneous. Okay? You do a problem like this in the video problems, but think about it. What kind of reaction, what's an example of a reaction that is exothermic and increases disorder? combustion, right? Think about it. You're taking something and you're emitting heat, so that means it's exothermic, and it creates a bunch of gas, so that means it's positive delta S. So combustion or burning things is always going to be spontaneous. At every temperature, it's going to be able to occur, okay? That's why I can burn some logs if it's negative 100 degrees outside, or if it's 100 degrees outside. It will always be spontaneous. This isn't always the case, right? Let's say I have something that has a positive delta H and a positive delta S. One example is melting ice, right? In order to melt ice, I need to put heat into it. That means it has a positive delta H. And notice what's happening. I'm going from something that's solid to something that's liquid. That's going to have a positive delta S. Well, in this case, I'm going to have a positive term, and then my negative T delta S term is going to be negative. Okay? So this will only be spontaneous if we have a high temperature, right? So this term right here will be really big. Okay? So melting ice is only spontaneous at high temperatures. Well, we know that's true because ice will melt if it's at 100 degrees or 200 degrees, but it won't melt if it's negative 50 degrees C. Let's look at an opposite kind of reaction. One where we have a negative delta H and a negative delta S. An example of this is melting or is freezing. So going from a water to ice, right? What am I doing? I'm going from liquid to solid. So I have a negative delta S. I'm decreasing disorder. But what do I do to do this? My Q is leaving. Heat is leaving. So that means it's exothermic. Okay? So this negative term makes delta H negative. The negative delta S means this negative T delta S term is positive. So this will be spontaneous, or delta G will be negative, only when this term right here, this T, is really low. So this reaction is only spontaneous at low temperatures. Well, we know that to be true. Because if I have water and I want to freeze it, what do? I put it at low temperatures, and then it will spontaneously freeze. Okay, so we can kind of just look at this and we can say, all right, based on delta H and delta S sign, we can figure out delta G. Okay? Now, I say here just high temperature and low temperature, and that's really relative. It depends on how big delta S and delta H are, right? So some reactions, what I call the high temperature, may not even be that high. Okay. All right, so let's do some examples. So we're asked, under what conditions, high or low temperature, are the following processes spontaneous? Okay. All right, so let's say we have this, a reaction with a positive delta H and a negative delta S. Okay. Well, I could just go to that last figure, but let's make sure we understand why this is the case. Okay. So we want to know delta G, whether it's positive or negative, based on these two. Okay? So delta G is going to be delta H minus T delta S. Right? So if I have a positive delta H and then minus T delta S, this is going to get me something that's positive. So I have a positive plus a positive, so that's going to get me something that's positive. Okay? That means it will never be spontaneous. No matter what the temperature is, this process will never be spontaneous. It'll never just occur. Okay, let's go on to B. B is water condensing. Now, I say water condensing. The first thing I have to always do on this is I need to go ahead and turn this into an equation. Okay, so it's water. And I say it's condensing. Condensing means it's going from gas to liquid. These are terminology we just need to know. Okay, condensing means gas to liquid. Okay, so what's the delta H here? Or actually, let's start with delta S. Delta S, we're going from something with high disorder to something with low disorder. Okay? This is more organized than this. Okay? So my delta S is going to be negative. Okay? Now, what about my delta H? Well, this reaction, I don't quite know, because I don't deal with this a lot. But what I deal with a lot in my kitchen is the opposite. I'll go from liquid to gas. That's called boiling water, right? So if I go from liquid to gas, well, what do I have to do? Do I have to put heat into this or take heat out of it? To go from liquid to gas, I need to put heat into it, right? So that means this has delta H that is positive. Okay? Well, what that means is, for the one I'm looking at, which is the reverse of this, my delta H will be negative. Okay? All right, so I have delta S negative and delta H negative. So what does that mean? Well, let's go up here and let's just put this right underneath, right? So for B, I said I have negative and negative, okay? So if it's negative and negative, okay, that's for delta H and delta S. So that means my delta H term is going to be negative, and my negative T delta S, this is going to be positive. Okay. So that means if T is really big, big T, right? So high temperature, this side is going to win out. So that means delta G will be positive. Whereas if T is low, right, then this will be bigger than this. So at low T temperature, delta G will be negative. What's this question asking for? It's asking for spontaneous. So this reaction is spontaneous at low temperature. Does that make sense? Well, yeah, because if I pull my cup outside and it's really hot outside, I'm not going to see anything. But if I put this glass outside and it's really cold, in the morning I start to see dew, right? I see condensation. Okay, so that's how we did. We looked at delta S and delta H. Now, why don't you go ahead and do these other three, right? So in the first one, or in C, you're given a reaction, so we need to figure out delta H and delta S. In the second one, we're actually given values, so we can actually calculate it. And then in E, we're asked about the combustion of coal. 2 carbons plus O2 going to 2CO, right? Now, we can figure out delta S from this. You need to be able to think, I'm combusting coal, so what does that mean my delta H is? All right, so come back, do that, and we'll discuss it later. Okay, so let's go ahead and let's look at this temperature dependence in one way, right? So remember I said that delta H, if I have delta H that's positive and delta S that's negative, it's always going to be non-spontaneous, right? So that means as I increase temperature, my delta G just becomes more and more positive. So it's never negative. So these are positive delta G's. These are negative delta G's. So no matter what the temperature, this reaction is always going to be positive. If I think of something that has a negative delta H and a positive delta S, this is something that's always going to be spontaneous no matter what the temperature, right? Whether I'm at 0 Kelvin or really high Kelvin, it's always going to give me a negative delta G. Okay? Now, there are some things where at low temperature, it's going to give me a positive delta G, but at higher temperature, it's now not going to be negative, right? And somewhere, I'm going to have something that's spontaneous at low temperature and not spontaneous at high temperature. All right. Okay, so let's go ahead and look at one other way to calculate delta G. And that is by using what's called the standard free energy of formation, or delta GF. And notice it has that not, meaning it's under standard conditions. Okay? So standard free energy of formation is similar to the enthalpy of formation, or standard entropy that we discussed last time. It's the free energy change for formation of 1 mole of a compound from its elements in their standard states, right? So taking H2O gas from its constituent elements, that's hydrogen and oxygen, in their normal state, right? We did this already for delta HF, and we did it for standard entropies, right? And these can actually just be calculated and put in tables, right? So this would be found in Appendix G of your book. And if I know the standard Gibbs free energy of formation, that's delta GF, I can use it to figure out delta G for any reaction in the same way I did for delta H and for delta S for enthalpy and entropy in the last couple of lessons. Okay? All right, so let's see how this works. Let's say we're asked to determine delta G for H2O liquid going to H2O gas. We're given some information from the back of the book, right? We have H2O liquid and gas. We're asked for delta G's, so we're going to use these. Okay? So I can go ahead and I can say, all right, H2O liquid and H2O gas, right? So I'm going to start off by doing delta G equals my delta G for my gas, my product first, negative 228.59 kilojoules per mole, minus the delta GF for the liquid, negative 237.1 kilojoules per mole. And when I do this, notice it's negative, and then this is negative and then negative, so I'm going to get 8.51 kilojoules. So this will be a non-spontaneous reaction under standard conditions. Remember, standard conditions are 25 degrees C, or 298 Kelvin, and liquid water doesn't boil, doesn't turn into gas at 25 degrees C. We know this. Okay? All right, now I kind of did this here without going to the board because this is the same as what we've done for delta H and for also delta S. Okay, we look and notice I have 1 and 1. That's because the stoichiometry of these is 1 to 1. If this were 2 and 1, we'd have to actually use that information. Okay, so let's go ahead and have you do one. This is a little bit trickier. We have Cr2O3 plus 3H2 going to form 2Cr solid plus 3 H2Os. And we're asked to do this based on, let me just fix this real quick. based on the delta GFs, okay, from Appendix G. I actually have already looked those up, and here they are. So you can look and you can see the delta GFs for CR203 is negative 1058.1. You can see it also for chromium, it's 0. For H2, it's also 0. And then we have H2O liquid right here. Okay. Well, why is this? Why is it that delta GF is 0 for chromium and for H2? That's because of the same reason that delta HF is 0. Remember, heats of formation and Gibbs free energy of formation are always forming that chromium from its constituent elements. Well, what's the constituent element of chromium? It's chromium. So I'm just doing chromium solid going to chromium solid. That's not a reaction, so it's 0. All right, so go ahead, do that, and then look over the video. Okay, so let's do one last thing on Gibbs free energy, and then we'll do an overview of thermodynamics in general. And that is, remember we said that at free energy 0, that is equilibrium, okay? That's the point where our reaction goes between, right? So you can see right here, for this reaction here, at this point, at this temperature, the reaction would be spontaneous in both directions. So that means both reactions are occurring. That's called equilibrium. And there's a special thing for when we're talking about phase transitions. That's going from solid to liquid or liquid to gas, right? Phase transition is the condition, the pressure and temperature, where it changes phase, right? And that is when delta G equals 0 for that reaction, right? It's going in both directions. And so we can talk about melting point, where we have solid going to liquid, or freezing point, liquid going to solid. These are the same thing, okay? Ice will melt at 0 degrees Celsius, but water will freeze at 0 degrees Celsius. So it depends on which way. The boiling point is also the same as condensation. Okay? So we can actually use that calculation of delta G in order to figure out melting points and boiling points. Okay? So remember I said that delta G equals 0 at these points. Well, delta G equals delta TH minus T delta S, okay? And I say this is 0. I could rearrange this to get me that. So I'm just going to add delta or T delta S to both sides. So I get delta H equals T delta S. I can rearrange this again to get the temperature is equal to delta H over delta S. Now, this isn't necessarily at standard conditions, but I can approximate this phase transition temperature by taking the standard entropy or standard enthalpy, delta H naught, and dividing by delta S naught, the standard entropy. Okay? All right, so let's go ahead and do this for water. So let's say we have the boiling, or we have water, and we're told delta H and we're told delta S. We can use these two values to figure out the boiling point. Okay. All right, so the temperature of the boiling point is going to be delta H naught over delta S naught. And it's actually, I can approximate it by it. It's not going to be exact, but it's going to be close enough. All right. All right, so my delta H is 44 kilojoules. And my delta S is 118.8 joules joules per K. Uh-oh, there's a problem. This is in kilojoules. This is in joules. So I need to go ahead and I need to convert. Okay. There's a reason why that one's sitting off to the side. So I have 44 kilojoules. And right here, this is 0.1188 kilojoules per Kelvin. Again, remember to go from joules to kilojoules. I divide by 1,000. And that's how I got that. Hopefully by now this is becoming second nature. Okay, so I can take this 44 divided by 0.1188. This is going to get me 370. Notice the kilojoules will cancel out, and I'll get 1 over Kelvin. So that's going to get me Kelvin. That makes sense. Now, this is what I approximate the boiling point of water to be, 370 Kelvin. What's it actually? Well, it's actually 100 degrees Celsius or 373 Kelvin. Okay. So it just gives me an approximation, but it's kind of nice to have another way to find boiling points. All right, so this is that work. We went ahead and we divided delta H by delta S, and we got our temperature in Kelvin. All right, so that is it for free energy. Okay, we talked about spontaneity. Remember, spontaneous means it just occurs. And we have two different ways to calculate delta G. One is using delta H minus T delta S, and the other is by using Gibbs formation. All right, and remember, delta G less than 0 is spontaneous, greater than 0, non-spontaneous. Okay, so before we go, I just want to do a little bit of an overview of thermodynamics. Okay, and I'm going to go ahead and I'm going to make a table of all of these constants we've talked so far. Okay? I'm going to talk about delta U, Q, W, and then delta H, S, and G. Okay, so I just had actually a change of heart. I was going to do this on the board behind me, but I figured it's easier to do it on the screen. All right, so we're going to go through them, all the terms that we've learned so far, figure out what it means to be positive, negative, and then how to determine it. This last part is very important, okay? All right, so the first term we talked about was delta U. Delta U is the internal energy change, right? So I have some system, whether it's water or whatever, and what happens to that, right? Is it gaining or losing energy? We only had really one way to figure that out. Delta U equals Q and plus W, right? This type of equation, looking at internal energy, this is going to be on quiz number 1. All right, so what's Q and W? Q is heat, okay? So a positive means that system gets heated, right? I take some water, I put it on the stove, it's being heated up. So negative means I take that water and I cool it down, right? Heat is leaving it. We can find this a couple ways. One is with calorimetry, okay? Where Q system equals negative Q surroundings. And in order to do that, we need to use specific heat, right? Where C equals Q over mass delta T. We also have work, right? Work is either surroundings, if that's work. W is work. W is work. If it does work, right? The system does work. That means it's either expanding or something like that. That means it's negative. W is negative. If work is done on a system, that means it's positive. Okay? We really didn't use work much. Only thing was delta U equals Q plus W. We also have delta H. Delta H is enthalpy change. If it's endothermic, that means it's positive. That means heat is going into the system. If it's exothermic, that means delta H is negative. That means it's giving off heat. This is combustion or fire. We can figure out delta H from calorimetry, or from Hess's law, or from delta HS. We also have delta S, that's entropy change. If delta S is positive, that means it's gaining entropy. So that means it's more disordered. Okay? Delta S negative means it's losing entropy. So that means it's becoming more organized. Okay? We can figure this out from standard entropies. We could also use Hess's law. In the same way Hess's law works for delta H, it actually also works for delta S. And then finally, we talked about delta G. Delta G is free energy change. The G stands for Gibbs free energy. And remember, delta G tells me whether something's spontaneous or not. If delta G ends up being negative, that means it's spontaneous. That means it's just gonna occur. And if it's non-spontaneous, that means it's positive, and that means it's not gonna occur. All right, so we can figure out delta G from delta G equals delta H minus T delta S, or Gibbs free energies of formation, or we can actually use Hess's law. In the same way we use Hess's law for delta H, we can also for delta S or for delta G. Okay, so there's one last video problem I want you to do, or I think you should do. Video problem 6C kind of goes through and it brings together delta H and delta S and also delta G. Okay? So let's say we have this reaction, SO2 plus 2OH going to H2SO4. Right? And we want to know delta G for it. Okay? We're given delta HFs and standard entropies. And we want to get delta G. So we're going to have to use equation number 1 up here to figure delta H for this reaction. We're going to use this equation number 2 to figure out delta S. And then you can use the fourth equation here to use that delta H and delta S that you just found, right, to figure out delta G. Okay? One hint, notice that I have this knot here. So that means I want this to occur at 298 Kelvin, right? So I'm going to use this 298 Kelvin for my temperature. All right, so go ahead and do this, and this will be kind of a review. All right, so just remember that this is the schedule for this week and next week. Exam number 1, which is on lessons 1 through 6, is on April 27th. That's a Monday. And quiz number 1 is on April 22nd. It's through Blackboard. You have to do it. By the way, this is Zoom on 422. We'll cover lessons 4 through 6. Okay? So quiz number 1 is on April 22nd. All right. Talk to you later.